Hello, my AP Chemers. Last time we talked about electrochemical cells, and we built an electrochemical cell or a battery from copper and zinc electrodes. And we looked at what happens in the reaction at the cathode and the anode, and we talked about the cell potential. One last thing that I would like to add, that we can, instead of drawing all this, we can use a line notation as a shortcut. I haven't seen this on the AP exam in a very long time, but I do want you to have it in your notes for when you go to college or if you see a problem like that on the worksheets. So when you do the line notation for a cell, what you do is you draw a line, and then you draw or write the symbol for the metal that's at the anode. And so in this case, it was zinc. Then you draw another line and write the ions that are at your anode. And so the ions that matter, which in this case are the zinc ions. So we don't really care about the nitrates. So you write Zn2+. Then you're going to do two lines, and that's going to separate your anode from your cathode. So then for your cathode, you're going to start with your ions, and so we have Cu2+, and then a line, and then the actual metal at the cathode, and then a line to end it. So this is your anode, and then this is your cathode. So that's just a shortcut to show you the different species in a battery. By drawing the line notation. Let's look at some terminology that we would use when we're talking about batteries. So what happens is that the electrons at the anode are driven by this electromotive force, EMF for short, and this electromotive force is basically your cell potential, it's your voltage. And it's because of a difference in the electric potential between your metals. So if you remember, we had looked at this table of standard reduction potentials, and we saw that different substances have different reduction potentials. And so because of that difference in the potential, you get a certain voltage, you get a certain force that forces the electrons to go from the anode to the cathode because of that difference. And again, that difference is your basically cell potential or your voltage of your battery. The electrons are flowing from high to low energy, which again is the anode to the cathode. A Coulomb is the SI unit for charge. Remember we talked about Coulomb's law. So Coulomb's law had to do with the attraction of positives and negatives or charges. So a Coulomb is a unit of charge. It's named after a scientist. A Coulomb is equivalent to 6.25 times 10 to the 18th electron, so it's equivalent to the charge of that many electrons. It's a lot of electrons. Or you can think about it the other way. One electron has 1.6 times 10 to the negative 19th of a Coulomb. So one electron has a very, very, very small charge. A volt is a measure of the difference in electric potential between 2 points, like we said. And so it's the unit of electrical potential. A volt is the same thing as a joule per coulomb, so it's energy per charge. 1 joule of work is needed to move 1 coulomb of electrons through a potential difference of 1 volt. And again, the high potential here is the anode. The low potential is the cathode in an electrochemical cell. If I double the amount of my substances, I don't change the voltage of the battery. That's because it's joules per coulomb. So if I double the amount of substance, then I double my amount of joules, but I also double my amount of coulombs. And so my voltage stays the same. And we'll talk more about that in a minute. An ampere is a unit of current. A current flow of 1 coulomb per second is what an ampere is. So let's actually get that down. An ampere is equal to a coulomb per second, 1 coulomb per second. And remember we said that a Coulomb is 6.25 times 10 to the 18th electrons. And so an ampere, since it's a Coulomb per second, is 6.25 times 10 to the 18th electrons per second, or the charge of that many electrons per second. A Faraday is the charge of 1 mole of electrons, and that is equivalent to 96,500 coulombs. So there's a lot there. We will use some of these in a little bit, as you'll see. To determine the cell potential, so the voltage of your battery, like we've done in the battery that we had here, what we did was we added the potential at the anode plus the potential at the cathode, and that gives you the total potential of the battery of the cell. And so that's how you calculate your cell potential, or your voltage of your cell, by adding the potential at the anode plus the potential at the cathode. A couple of things to keep in mind in terms of that potential, that cell potential. So when we looked at our potentials, we are always given reduction potentials, as we talked about in the last lesson. These are all reduction equations. We're gaining electrons. And so that's something to keep in mind. The higher the positive value in terms of that reduction potential, the more likely it's going to be reduced. The lower the value, the more likely it's going to be oxidized, or the less likely it's going to be reduced. So that's what this is saying right here. So when the reduction potential is positive, these are the ones that are most likely to be reduced. The negative values, these are least likely to be reduced, which means they are most likely to be oxidized. Another thing to keep in mind is that these are all reduction potentials that are on the table. So if you have an oxidation reaction, you want to flip the potential. So for example, when you look at your table to look at zinc, you'll see the reduction of zinc, like we did in the last video. And so zinc right here, you see the reduction, zinc 2 plus 2 electrons yields neutral zinc. The potential is negative 0.76. That's your reduction potential. So this is negative 0.76 volts. If you are, and I apologize, this should be nothing there, it's a typo. That should be neutral zinc. If you are flipping the reaction so that you have an oxidation reaction, if you're oxidizing zinc to go from neutral zinc to zinc 2 plus, then you have to flip the sign of the potential, and so it's going to be positive 0.76 volts. Potentials are intensive. They do not depend on the quantity. So you do not multiply by the coefficient. That's what I was talking about here. If you have more of your substance, the voltage remains the same. So if I'm given this reaction, F2 plus 2 electrons yields 2F minus, I'm reducing my fluorine here. Let's look up the reduction potential for that. That is 2.87 volts. So 2.87 volts. If I double my reaction, I do not double my voltage. It is still 2.87 volts. Again, the reason for that is because voltage is basically energy per charge. And so if I double the amount of fluorine that I have, then I have twice as many joules, but I also have twice as much charge, or twice as many coulombs. And so both of them increase by the same amount, and so your ratio remains the same. It's kind of like density, how density is mass per volume. So if you double your amount, you double your mass, you double your volume, but your density remains the same because it's the ratio between them. So it's the same idea here. The voltage remains the same even if you double your reaction, or triple it, or do whatever to it. So let's do some examples here where we are trying to solve for the cell potential. So we want to determine the potential of a galvanic cell, and here's the equation for it. We want to write the overall balanced equation. So this is not balanced. We want to balance it. And then we also want to find the potential. So first, you want to split it up into the two equations. So we have Fe3 plus going to Fe2 plus, and we have Cu solid going to Cu2 plus. So if you remember when we used to balance these, you'd balance anything like your atoms themselves first. So one iron, we're good. Then you balance the charge by adding electrons. And so you add electrons because electrons are negative. You always add electrons to the more positive side. So we're going to add an electron here. And we are going to look up the potential for that on our table. And so this is, let's see, do we have that one with the iron? Right here. That's the one. So the potential is 0.77 volts. So we're going to write that down. Okay, the next one is actually an oxidation. We're going from copper to copper 2 plus, so we're going to add 2 electrons here. So be careful because this is oxidation. When we look up the potential, we want to flip it. So we have copper neutral and copper 2 plus, so let's find it on our table. That would be this one, copper neutral to copper 2 plus. Remember, this is reduction. We are looking at the oxidation, so we're going to flip it to go from copper to copper 2 plus. So we also flip the voltage, so this says positive, so we're going to make it negative 0.34 volts. Okay, we want the overall balanced reaction, so that means we want to add these two equations. In order to add them together, we have to equalize the electrons. Remember that when we were balancing redox reactions. So that means we need to multiply this reaction by 2. So when we multiply by 2, we'd get 2, 2, and 2. Remember, you leave your potential as is. You do not multiply your potential by 2. It is intensive. So then we add it up. So we can cross this out with this one. Your electrons will always cancel if you do it correctly. So 2Fe3 plus Cu yields 2Fe2 plus Cu2 plus. That should be balanced. Let's double check. We have 2 irons on both sides, 1 copper on both sides, and then check the charge as well. This is 2 times 3 plus is plus 6. On this side we have 4 plus and 2 plus is plus 6, so it is balanced. Your cell potential would be these two added together, so the total is 0.43 volts. If you are doing this correctly and it's an electrochemical cell, your cell potential will always be positive. You should never have a negative voltage in a battery. When we do electrolytic cells, your cell potential will be negative. But for electrochemical cells, because it's spontaneous, because it's product favored, because it's a reaction that will occur and the electrons are flowing in the normal direction that they would like to, your cell potential should always be positive. So if you get a negative cell potential for an electrochemical cell, something went wrong. The line notation for this one is going to be, we're going to start with a line. Our anode comes first, and so that's what's oxidized. So this is your anode because that's your oxidation. This is your cathode, so that's your reduction. So the metal here is copper. Then our ions are Cu2 pluses. And then double line between the anode and the cathode. At the cathode we have Fe3 pluses and Fe2 pluses. They're both ions, right? So you put them both together where you put the ions. And then now what metal would you put there? there is no metal, right? This is an ion, this is an ion, so these are salts basically, right? It's probably iron 3 nitrate, iron 2 nitrate. They're salts, they are not solids. We need a metal solid to be our electrode. And so when you don't have anything, you put platinum as your electrode. Platinum is a metal that will conduct electricity, but it is inert. That means it's very, very stable. It does not really participate in any reaction. And so usually we use platinum or gold or something like that as our electrode when we just have ions there participating in the reaction. And so platinum is what you want to put down. Let's try one more here. It says, given the following cell, write the reaction at each electrode and the overall equation. Calculate the cell potential and draw the line notation. And they give us this reaction here. So let's look at what's happening in this reaction. So we are given copper, going to copper 2+, we're going to split it up. And the other one is Cr2O7 2- going to Cr3+. Now, to be honest with you, you can balance these, or you can just kind of cheat and look them up. It's not really cheating because you have to be given the cell potentials, and the cell potentials come with the equations. They can't just give you the potential, they always give you the equation and the potential. So if you want to balance it on your own, you're welcome to. If you just want to copy it, you're welcome to. But for this one, you're going to need to add 2 electrons, and this is an oxidation, right? And so let's look at our table here. We have Cu and Cu2+, which is this one right here, but it's an oxidation, so this is flipped. So we're going to flip our voltage. So let's write that down. Our potential is negative 0.34 volts. So that's this one. Let's look at the next one. The next one has oxygen in it, and remember I told you back when we did chapters 3 and 4 that you do not need to balance things like redox reactions that have oxygens and hydrogens, and this one does, right? If you really want to, you're welcome to balance it, or you can just copy it down. So let me show you where it is. So this has oxygens and hydrogens, so it's going to be one of these. I'm going to go ahead and flip this so that we're able to see it a little bit better. And so we are going from Cr2O7 2- to Cr3+, and it's a reduction equation. So we're looking for one that has the dichromate ion and going to Cr2+. So I see a chromate here, that's not the dichromate. Let's keep looking. Oh, let's go to the first page here. There we go. So we want to keep looking until we find it, and here it is. Dichromate giving off Cr3+ in electrons, right? Gaining electrons, it's a reduction. So again, you can balance it if you'd like, or you can just copy this off. It's going to be given to you on the test, so you can just write it down. So I'm going to go ahead and copy this. So the equation here is Cr2O7 plus 14 H pluses plus 6 electrons yield Cr3+, 2 of those plus 7 H2O, and your potential is 1.33 volts. Okay, we've got both half reactions. So now what we want to do is equalize the number of electrons. So there are 2 electrons here that are being given off. There are 6 electrons here that are being gained. We can't have that. The same number of electrons need to be transferred, right? And so 6 and 2, so we need to multiply this by 3. So I'm going to go ahead and do that. So 3 Cu yields 3 Cu2 plus 6 electrons. Remember, your potential remains the same. You don't multiply it by anything. Okay. When you add them together now, you are going to add the reactants, which is these, and then arrow, and then you're going to put your products in. So I see 6 electrons on the product side. I see 6 electrons on the reactant side, so I'm going to add the rest. 3 Cu plus 14 H plus Cr2O7 minus yields 3 Cu2 plus 2 Cr3 plus 7 H2O. If you check, you should see that it balances. So 3 coppers, 14 hydrogens, 7 oxygens, 2 chromiums. Let's check the charge. Plus 14 minus 2 is plus 12. On this side we have plus 6 and plus 6, so that's plus 12. So that's balanced. That's your overall reaction. The overall cell potential is going to be the negative 0.34 volts plus 1.33 volts. So your cell potential is going to be 0.99 volts. Last thing we need to do is the cell notation, or sorry, the line notation, I'm sorry. So this is the oxidation, this is the anode, this is the cathode where the reduction occurs. So we're going to start with our anode. And so let's see what we have at our anode. The metal that we have at our anode is copper. The ions that we have are Cu2 pluses. Double line. What ions do we have here? Well, we have the dichromate ion. And we also have the Cr3 plus ions. Both of those are ions, right? So then what metal do we have? Well, since we don't have a metal here, we're going to use platinum as our metal.